Hi children, welcome to my channel Think Maths. As you all know, we are dealing with NCERT Class 10 Maths Chapter 1 Real Numbers. In this session, we are going to discuss about irrational numbers, Theorem 1.3, 1.4 and example 9, 10, 11. If you are able to follow my classes, just like, share and subscribe. Only your support motivates me. Okay children? So let us get into the classes. So first is irrational number. So what is a irrational number? So a number is called irrational if it cannot be written in the form p by q, where p and q are integers and q not equal to 0. So it is noted as q bar. So examples of irrational numbers are root 2, root 3, pi, etc. Okay. So that is irrational numbers are numbers which cannot be written in the form p by q. So if we cannot write in the form 2 by 3, 4 by 5, we call those numbers as irrational numbers. Okay. So these numbers are called rational numbers. So the fractions are called rational numbers. Okay. So now we are going to see about irrational number. So it is denoted by the symbol q bar. So examples for this are root 2, root 3, pi, etc. Okay. So let me go to theorem 1.3. So theorem 1.3 says that let p be a prime number. If p divides a square, then p divides a, where a is a positive integer. So before explaining this with p and a, let me explain this theorem with the numbers. So let me take a number of our class, that is 10. So I take a is equal to 10. So 10 can be factorized as 2 into 5. Okay. So a square. So a square is nothing but 10 square. That is 10 into 10. So this 10 into 10 can also be factorized as 2 into 5. Again 2 into 5. So this is nothing but 2 power 2 into 5 power 2. Okay. So here 10 is a, 2 and 5 are prime numbers. So we take a is equal to p1, p2, etc. pn. Okay. So here p1, p2 are 2, 5. Okay. For a square also it appears as p1 square into p2 square. So we can say that if p divides a square, so I take one of the prime number p2. So I take prime number 2. Okay. So they gave p divides a square, that is 2 divides a square. So here a square is 100. So 2 divides 100. So the same 2 appears here. Okay. So even in the factorization of a square and a, the prime numbers are not different. So they are same. Just here the prime numbers are repeated twice. Okay. So 2 and 5 appears both in the prime factorization of a as well as a square. So we can automatically say that if 2 divides 100, that is 2 will be in the prime factorization of 100. Okay. So then the same 2 will be in the prime factorization of 10. Okay. So we can say that this 2 also divides a. That is 2 divides 10. Okay. So this is what we have to prove with the values p and a. Okay. So let's go to the problem. So let the prime factorization of A be A is equal to P1, P2, etc. Pn. Okay, we took here A is equal to 10. Their prime factorization are 2 and 5. So that is P1 and P2 are 2 and 5. So where P1, P2, P3, etc. Pn are primes, not necessarily distinct. Okay. So next A square. So A square is nothing but 10 square. So 10 square is nothing but 10 into 10. So 10 into 10 we can factorize as 2 into 5. Again 10 can be factorized as 2 into 5. So this is nothing but P1 square into P2 square. That is 2 square into 5 square. This is what we done in using numbers. So same is repeated here using the values P1, P2, etc. Pn and A. So we have to prove that P divides A if P divides A square. Okay children. So given that P divides A square. Okay. So by fundamental theorem of arithmetic, P is one of the prime factors of A square. So if P divides A square, if you factorize A square, this P appears there, right? So that is, we took A square as 10 square. So 10 square is nothing but 2 square into 5 square. So by fundamental theorem of arithmetic, P. So I took P as 2. So P will be one of the prime factors of 10 square. Okay. This prime factor will be unique. Okay. By using uniqueness of the fundamental theorem of arithmetic, the only prime factors are P1, P2. So the prime factors will be only 2 and 5. Okay. So P will be in any one of the form. So in this P1, P2, etc. Pn, this P appears in this. So we took A as P1, P2, P3, Pn. Okay. Then this P will appear here. Okay. So then P divides A. Can you understand? So that is 10 square equal to 2 square into 5 square. Even 10 is equal to 2 into 5. Okay. Here no other prime factor appears. Whatever the prime factor appears in 10 square, the same prime factor appears here. So the prime factors are not different. So the only prime factors are 2 and 5. That is the only prime factors are P1, P2, P3, etc. Pn. So A, we define A as P1 to Pn. Then we can say that this prime, the same prime factor which appeared in A square appears in A. So we can say that P divides A. Okay children. Let me go to next theorem. We have to prove that root 2 is irrational. Here we are going to take a contradiction. That is root 2 is rational. So what do you mean by rational? Rational is nothing but we can express this as fractions. That is R by S. Suppose this R and S have the common factor. That is, I can say that root 2 is equal to 20 by 25. That is, here R is equal to 20, S is equal to 25. So they both have the common factor 5. So if I divide by 5, I get root 2 is equal to 4 by 5. Okay. So I divided by 5. So this 4 and 5 are co-prime. That is, they are divisible by 1. So they are co-prime. So this co-prime can be expressed as A and B. So A and B are co-prime. Okay. So root 2 is equal to A by B. So that is A is equal to root 2B. So A square, squaring on both sides, we get A square equal to 2B. So A square is nothing but product of 2. Okay, so that is multiplied by 2. So we can say that this 2 divides a square. 2 divides a square. We already proved that if p divides a square, then p divides a. So by theorem 1.3, we can say that 2 divides a. Okay. So if 2 divides a, then a will be a multiple of 2. So we can write that a is equal to 2c, where c is some integer. Okay. So I am going to substitute a is equal to 2c in this equation. Okay. So if we substitute this in this equation, we get 2c whole square equal to, that is here if we square, we get 2b square. Okay. It is equal to 2b square. So 2c whole square is 4c square, which is equal to 2b square. So dividing by 2 on both sides, we get 2c square equal to b square. So we can say that b square is a multiple of 2. That is 2 divides b square. 2 divides b square, right? So in the same way, by theorem 1.3, I can say that 2 divides b. So we got that 2 divides b as well as 2 divides a. But what did we assume for a and b? We assumed that a and b are co-prime. Okay. So I divided by the common factor. So we got a and b are co-prime, that is divisible only by 1. Here we got the common factor as 2. But this contradicts that a and b are co-prime. So this problem exists because we assumed that root 2 is rational. So our assumption is wrong. So root 2 is irrational. Can you understand? So we can write the problem. So we assume that root 2 be rational. So rational number can be expressed as fractions. Root 2 equal to r by s. If r and s has the common factor, then if we divide by the common factor, we get root 2 is equal to a and b. Then a and b will be co-prime. So root 2 is equal to a by b. So a will be equal to root 2b. So squaring on both sides, we get a square equal to 2b square. So this shows that 2 divides a square. So by theorem 1.3, 2 divides a. This a is a multiple of 2. So we can write a is equal to 2. 2c. So if we substitute a is equal to 2c in this equation, we are getting 2c square equal to b square. So this shows that 2 divides b square. So by theorem 1.3, 2 divides b. So these two lines show that 2 is the common factor for a and b. But we got that a and b are co-prime. That is, their common factor is 1. So this contradiction came as we assumed that root 2 is rational. So our assumption is wrong. Though, so we can say that root 2 is a irrational number. Okay. So in the same way, we can prove for root 3. So example 9, we have to prove that root 3 is irrational. This is same as the theorem 1.4. In theorem 1.4, we already proved that root 2 is irrational. So same method has to be followed. So we have to prove that root 3 is irrational. So contradiction. Let root 3 be rational number. So rational number means we can write as r by s. Suppose r and s have a common factor other than 1. So we can divide by the common factor and we get root 3 is equal to a by b, where a and b will be co-prime. Okay. So root 3 is equal to a by b. Then when b comes to the left hand side, we get a is equal to root 3b. Okay, children. So as usual, we have to square on both sides. If we square on both sides, what will we get? We get a square equal to 3b square. Okay. Squaring on both sides, a square equal to 3b square. So this means that this 3 divides a square because a square is a multiple of 3. So we can say that 3 divides a square. Okay, by theorem 1.3, 3 divides a. So 3 divides a means a is a multiple of 3. So a is equal to 3c for some integer. So we are going to substitute a is equal to 3c in equation 1. So if we substitute instead of a 3c, we get 3c whole square equal to 3b square. So 3c whole square is 9c square equal to 3b square. So dividing by 3 on both sides. So 9 divided by 3 is 3. So 3c square equal to b square. So this equation shows that 3 divides b square. Okay. So by theorem 1.3, we get 3 divides b. So these two statements show that 3 is the common factor for a and b. But we showed that a and b are co-prime. Okay. We showed that a and b are co-prime. So but we got a common factor 3. So this contradiction came as we assumed that root 3 is rational. But our contradiction is wrong. So root 3 is a irrational number. Okay, children, can you understand? So both theorem 1.4 and example 9 are same. Okay, so let us go to the next example. Example 10, show that 5 minus root 3 is irrational. Here also we are going to assume the contradiction, that is 5 minus root 3 be rational. So we can find the co-prime a and b, so that 5 minus root 3 will be equal to a by b. So I take root 3 to the right hand side and a by b to the left hand side. So we get 5 minus a by b is equal to root 3. Since this a and b are co-prime, that is, we can say that a by b is nothing but 2 by 3. That is 5 minus 2 by 3. Okay. So this is of the form like this. So if we factorize this, we get 3 as the LCM. 5 minus 3, 15. 15 minus 2. So 15 minus 2 is 13. So 13 by 3. So we got as fractions. Okay. So 13 by 3 is a rational number. So but we proved that root 3 is irrational. Okay. So we proved that root 3 is irrational, but we got 5 minus a by b as a rational number. So our assumption is wrong. So 5 minus root 3 is irrational. Okay, children, can you understand? So since a and b are co-prime, we get 5 minus a by b is rational. So root 3 also will be rational, but we already proved that root 3 is irrational. So our assumption is wrong. So 5 minus root 3 is irrational. Okay, children. So next problem. Example 11. Show that 3 root 2 is irrational. This is of example 10. So we have to assume the contradiction. Let 3 root 2 be rational number. Then we can find the co-prime a and b such that 3 root 2 is equal to a by b. So I take root 2 in LHS. 3 is in numerator. When it comes to RHS, it will be in denominator. Since a and b are co-prime and 3 is also an integer, this a by 3b will be a rational number. If this is a rational number, then root 2 will also be a rational number. But we already proved that root 2 is irrational. So our assumption is wrong. Therefore, 3 root 2 is a irrational number. Okay, children. That's all for this session. Thank you for watching my video. So if you are interested, just subscribe to Think Maths.